Question 2. Chlorine is a reactive yellow-green gas. It is a strong oxidizing agent. But state how chlorine is used in the purification of water. This one is used to kill bacteria. Okay, it kills bacteria, or we can say microorganisms. So the species that is actually responsible for this, we see chlorine here reacting with water, and then you get HCl, then plus the hypochlorous acid. This one here is the one which is responsible for the killing of the bacteria. The OCl minus, or sometimes people write ClO minus, something like that. This one is the one that is responsible for the killing of bacteria. Okay, then part B. Chlorine has the highest first ionization energy of period 3 elements. From sodium to chlorine. Construct an equation for the first ionization energy of chlorine. Include the state symbols. You see here they are saying include. So usually when they tell you to write the equation, it is not always a must to put the state symbols. But for ionization energies, it is very important that even if they don't put it, you have to make sure that you put the required state symbols. Now, for first ionization energy, we look at the energy required to remove 1 mole of electrons from 1 mole of a gaseous atom to form 1 mole of 1 plus gaseous ions. Okay, so I will have chlorine. It has to be a gaseous atom. Chlorine is a gaseous diatomic molecule, but here it has to be split, and then you get only 1 chlorine atom. And then here you are removing an electron, so this one has to be positively charged, a gaseous 1 plus ion. Okay, and then the electron here which is lost. Of course, this one is a minus, and then this is a plus, so they balance. No overall charge, no overall charge this side. As simple as that. Okay, then next, Roman 2. Explain the general increase in the first ionization energies of period 3 elements. First of all, there is increase in proton number. When the proton number increases, then that means that the nuclear charge. Remember, the nucleus has gotten protons which are positively charged, and then the neutrons which do not have any charge. So when you increase the number of protons, that means the charge in the nucleus increases. So that's why we say the increase in the nuclear charge. You see that? And then from there, since you are adding electrons on the same shell, you are adding them there on the same shell, as protons are also being increased, then that means that the shielding is similar. If I have a shell of electrons here, the shielding is the same. Shielding is just the repulsion between these electrons. Okay, so it is similar all throughout. But if you are adding shells, the shielding always increases because each shell that you are adding there is repelling the electrons on the outermost shell. Does that make sense? Okay, so since the shielding is similar all through, then there is going to be a greater attraction of the nucleus for the outer electrons. So what will I say here? Increasing nuclear charge. Increasing nuclear charge due to increasing proton number. Okay, but similar shielding. Why? Since electrons are added to the same shell, since electrons are added to the same shell, so what? Greater attraction, therefore greater attraction of the nucleus. We can say nuclear attraction for the valence electrons. Okay, So therefore, greater attraction of the nucleus for the outer or valency electrons. So what is so important is to tell us about the nuclear charge that is increasing due to the proton number, and then similar shielding has to appear in there, therefore greater attraction. So this greater attraction is the one that is responsible for providing high ionization energy to overcome it. Okay, so that is that. Part C, the halide ions, we have the ones for chlorine, bromine, and iodine, show clear trends in their physical and chemical properties. Roman 1, state and explain the relative thermostabilities of the hydrogen halides. Okay, relative thermostabilities. Of course, the thermostability decreases down the group. Like as you go down the group, it takes very little energy for you to break down these compounds. So I'll say thermostability decreases down the group. Okay, this HX bond energy, okay, it's bond energy decreases. So bond energy decreases down the group. Okay, why? This is due to decreased nuclear charge. Decreased nuclear, not nuclear charge, nuclear attraction for the bonding electrons. Now, thermostability decreases down the group. The explanation, the bond energies decrease, but this is how it is. So I've added this one just to explain where this one comes from. I have, let's say, iodine. This is the nucleus, but then the outermost shell electron is there. This one is maybe bonding with the hydrogen, so they are sharing electrons. Then we have chlorine, which is smaller in size, so the nucleus is nearer here. So this is chlorine, and here you have iodine. So the distance between the nucleus here and the bonding electrons is far much bigger than the distance between here. You see that? So since this distance is far bigger, the attraction between this nucleus and the electrons here is weaker than the attraction here. So that's why this one, because the attraction here is stronger, it will need much more heat to break it down compared to this one here. That's why when you go down the group, the thermostability decreases. If something is thermally stable, then that means that it requires a lot of heat to break it down. Okay, so that is that. Then here they are saying the halide ions react easily with concentrated sulfuric acid. The main sulfur-containing product of each reaction is shown in the table. For chlorine, it is hydrogen sulfate, and then here it is sulfur dioxide and then hydrogen sulfide. Actually, for iodine, we have these three equations. Let me write them here. For iodine, you have iodine here, okay, reacting with sulfuric acid. So the first reaction is acid base. Then you get hydrogen iodide, then plus this one is going to be, it's not actually iodine. Let me write, let's say sodium iodide. Okay, sodium iodide, pardon me here. We are even seeing these ions here. Okay, then from there we shall have now sodium hydrogen sulfate. Then the next one, because this one is thermally unstable and it is more of a reducing agent compared to sulfuric acid, then there is going to be a reaction between the two. So sulfur, sulfuric acid is going to now oxidize this one. So we shall have this one here now reacting with sulfuric acid, and then it can give you iodine. Then we have sulfur dioxide and then water. The other one is iodine, then plus sulfur, then plus water. Then the other one can be iodine, then plus hydrogen sulfide, then plus water. For hydrogen bromide, if here we had bromine, okay, it is only this one. Here you get bromine, then sulfur dioxide, and then water. But for iodine, it goes further and then gives you the sulfur or maybe the hydrogen sulfide. Okay. They are telling us that the main sulfur-containing product for the reaction of concentrated sulfuric acid with chlorine is this one, hydrogen sulfate. Remember, there is also HCl, but this one is not broken down. Here there is. Now the HBr is broken down, and then you have the bromine, then the sulfur dioxide, okay, and then the water. Then here you also have iodine, hydrogen sulfide, and then water, okay? That is what you should know there. So let's check the oxidation number of sulfur in here. What are we going to have? We have 1, that is the oxidation number of hydrogen, then plus the 1 of sulfur, we don't know. And then we have 4 oxygens, but each of them has the oxidation number as a -2. And then here we equate to -1. The total charge here is -1. Now this is -8, okay? Plus 1, that will be -7. When -7 comes this side, it will become a plus. Then you have -1 plus the 7. Isn't that one +6? That will be a +6. So we shall have +6 here. And then here, we are going to have N for sulfur. These are 2 oxygens. Each of them is -2 here. And then we equate this one to 0 because there is no overall charge here. This is -4. N minus 4 is equal to 0. When the 4 crosses, it becomes a +4. Okay? Now you can see right from here that if you have this one as a +6 and then here it's a +4, that is a reduction. So this one has been reduced. It has oxidized this one because this one has moved from -1 then to 0, because here the oxidation state of iodine is 0, or even for bromine. Same reaction, okay? So that is that. It's a redox reaction. Then the oxidation state of sulfur in here, we have 2. Then, 2 times 1, because we have 2 hydrogens. Then plus this one is N is equal to 0. What will be the N here? It will be a -2. So we shall put a -2 there. Now, what are they saying here? Complete the table, we are done. Then explain why different sulfur-containing products are produced when each of these halides, halide ions reacts with concentrated sulfuric acid. So I will say halides are better reducing agents as you go down the group, okay? They are reduced. So halides are weaker oxidizing agents, in other words, are weaker oxidizing agents down the group. Another person can say halides are stronger reducing agents, okay, down the group. A reaction becomes so fast if there is a reducing agent, strong oxidizing agent. So sulfuric acid is a strong oxidizing agent. Then we see a bromide here or an iodide, they are strong reducing agents. Okay. Now, reducing agent is the one which gets what? Oxidized. In other words, it releases electrons. It loses electrons. Okay. And to get oxidized is to lose electrons. So it loses electrons and it gives them to the other. Okay. So because the other gets reduced by receiving electrons, then the one that has given electrons is the reducing agent. When you are in contact with them, they give you the electrons, you are reduced. As simple as that. Remember, these halides react by gaining electrons. Not so. They gain an electron. But as you go down the group, the distance here is too big. That means the attraction between the nucleus and this electron becomes very weak. Okay? So it becomes so hard for them to receive electrons, but rather to lose them. But it becomes very easy for smaller ions like chlorine, these atoms like chlorine, for it, the distance between the nucleus and the electrons is very short. The distance is very, very short, so the attraction becomes stronger. So it is easier for them for like chlorine to receive an electron, and therefore it's an oxidizing agent. Okay, because an oxidizing agent gets reduced, therefore it attracts electrons to itself. I don't know whether that made sense. So that is that. Now, part D, chlorine reacts with aqueous sodium hydroxide in a disproportionation reaction. Roman 1, state what is meant by a disproportionation reaction. Of course, here we see a reaction where one species is both oxidized and reduced. So this is a reaction where a species is both oxidized and reduced. Both oxidized and reduced. Write an equation for the reaction of chlorine with cold. If it is cold, I will have my chlorine here reacting with sodium hydroxide, and then we shall have sodium chloride, then plus sodium chlorate 1, sodium chlorate 1, then plus water. Okay, to balance this, the chlorines are 2, even here they are 2, and then sodiums, we can see 1 here and then 1 here, those are 2. Suppose I put a 2 here, then oxygen will even be 2. This is 1, those are 2. Hydrogens are 2, hydrogens are 2, so that is balanced. Now, with hot, okay, with hot conch, then sodium hydroxide, this is what you get. You get chlorine plus that sodium hydroxide. You still get sodium chloride, but then here you get sodium perchlorate, so with the 3, and then water. This is the one you get. Okay, so you can balance this one. So with hot, it has to be this one here. Okay, with cold, sodium chloride and water, then sodium chlorate 1. With hot, you have sodium chloride, water, and then perchlorate. You just put a 3 here. The balancing is left for you. Okay, so that is that. Part E, aluminium reacts with chlorine to form aluminium chloride. Aluminium chloride can exist as the gaseous molecule. This one is a dimer. This molecule contains coordinate bonds. And then they say that draw the diagram that clearly shows all the types of bonds, types of bond present in this dimer here. So I will have aluminium here, and then I have another aluminium here, then 6 chlorine atoms. Just place them just like that. So this aluminium chloride is electron deficient. So I can do that. They have shared the 2 electrons, 2 electrons, 2 electrons. The hydrated compound of aluminium chloride is an ionic compound, but then without any water, if it is a gaseous molecule, then it is going to dimerize. Okay, so what is going to happen is that, let's say these are 2 electrons shared here, 2, 2, 2, 2, those are 6. So it is remaining with 2, and chlorine here has already shared with this, but then it has lone pairs. So what happens, it donates a lone pair here to this aluminium. Okay, The same with this one here, it will donate to this aluminium. So we write something like this. You put here, and you can put an arrow here, and then here you also put an arrow, meaning one lone pair here is given to this aluminium here, which is electron deficient. It doesn't matter whether, sometimes you might find when they have put the arrow here, and then for this other one it is here, it doesn't matter. Okay, so that is that. All right, then Roman 2. Of course, these are covalent bonds, these ones which are left this way. All of them are covalent bonds, but we are seeing coordinate bond. So in the coordinate bond, yes, we are seeing the sharing of these electrons, but these two electrons are coming from one species. Okay, for just covalent bond in general, they are sharing electrons. Okay, so between the two atoms, let's say this one is bringing, this one is bringing, but then for dative, the two electrons are being shared, but they are coming from one species. Roman 2. Describe what you would see when solid aluminium chloride reacts with water. Name the type of reaction that occurs. Of course, the type of reaction is hydrolysis, because this dimer is going to be broken down. So when this dimer is broken down, we are going to see these ions, and since aluminium 3 plus here, this one is, it has a high charge density, it has a smaller size, but then the high charge, it is going to have a very high charge density. So this one is going to cause the water molecules that are surrounding it, okay, the water molecules in here, to lose a hydrogen. Okay, so this one will be lost. Okay, so when this hydrogen is lost, then the hydrogen ions that are lost in this solution, they are going to make this solution acidic. Okay, so we are going to see an acidic solution. So in my book here, there is something here about the effect of water on chlorides of period 3 elements. Remember, this is the structure that we have just seen. Okay, you can see the pair of electrons shared by chlorine with aluminium here, which is coming only from chlorine. The same thing here. Okay, and then it can be represented like this. I can put this one here and then this one here. Okay, that's the one I used, so it doesn't matter. Okay, then from there, there is something they are saying here, that once we add water, the dimers are broken down and the aluminium ions and chloride ions enter the solution. Each relatively small and highly charged aluminium ion is hydrated and causes a water molecule bonded to it to lose a hydrogen ion, thus turning the solution acidic. We can show this in an equation as follows. So here one water molecule is broken down. You have OH and then a hydrogen ion. You see that? So the OH now, OH minus is going to reduce that charge to a +2. That's why you're seeing a +2. And then the OH here, and then a hydrogen ion is here. So we are going to see this one is released in solution, so making it acidic. This one is going to continue until we have 3 OHs here and then 3 hydrogen ions. Okay, so that is that. So we are seeing this solid broken down. Okay, so we shall say that the solid disappears. Solid disappears. I think the spelling here has to be with a small, one S. The solid disappears. The reaction here is a hydrolysis one. The reaction is hydrolysis. Okay. Then they said that describe what you would see. So we would also see Mr. fumes. Mr. fumes, that is HCl. Okay, also increase in temperature. It is an exothermic reaction. Okay, but the one that you would see very fast is the solid to disappear. Okay, so we can stick on this and then the reaction is hydrolysis. Okay, so these ones I can just put them on as just additions. you have aluminium. When, of course, in the presence of water, now this one is broken down, we are now going to have aluminium chloride here, okay? Then plus water, this one is going to give us aluminium hydroxide, okay? Then plus the HCl. These are the Mr. fumes that are coming off, okay? So that is that. Then part F, they are saying that 0.02 moles of element Z reacts with chlorine to form 0.02 moles of the liquid chloride. The liquid chloride has the formula, this one here, where N is an integer. And then this formula here reacts vigorously, this compound reacts vigorously with water at room temperature to give an acidic solution and a white solid. When excess silver nitrate is added to the solution, then we are seeing 11.54 grams of silver chloride, which is formed. Roman 1 suggests the type of bonding and structure shown by this one here. Now, the fact that it reacts vigorously with water, then the bonding is covalent. The structure is simple. Okay, structure is simple. Okay, then the bonding has to be covalent. The bonding is covalent because it is the hydrolysis with water. The structure is simple because it is a liquid at room temperature. That means it has a low melting point. You see that? Then calculate the value of N in zinc, not zinc. Z here, then the chlorine, that compound there. So let's begin with the molecular mass of silver chloride, okay? Because they gave us the mass here that is given off. So this one is going to be silver is 107.9, okay? Then plus chlorine is 35.5. When you add these ones, what do you get? 107.9. Then plus 35.5, that is 143.4. 143.4. Okay, then moles of silver chloride. We shall get this 11.54. 11.54. Then we divide by the relative molecular mass here. Okay, and this one will give us 11.54 divided by 143.4. That one is giving us 0.08047. 0.08047. I'll maybe stop it there. Then I will look at zinc and chlorine. So, and then I take the mole ratio. Okay, the mole ratio. So the moles of zinc, not zinc, sorry, it is Z, okay? This is 0.02. And then the moles of chlorine. Remember, when this one reacts, when it is dissolved in water, it is going to give you silver and then the chloride, okay? So we shall take the moles of silver chloride here to be the same as the moles of what? The chloride. So we shall have 0.08047, and then which one is smaller is of course this one. This one 0.02. We divide it all through. This is 0.08, 0.02. That is 4. So this will be 1 to 4. So meaning we shall have zinc, not zinc. I don't know why I'm always saying zinc. So Z, then Cl, then this one will be 4. So N will be equal to 4. Part G, dichloromethane is widely used as an organic solvent. Dichloromethane can be prepared by reacting chloromethane and chlorine at room temperature. The reaction proceeds via several steps as shown. Initiation, this is the production of radicals, okay? So this chlorine bond here is broken down by UV light because this one is carried out under UV light, okay? And then from there, the radical which is produced now attacks a molecule to produce another radical and then a new molecule. Then that is now propagation. Again, the new the new radical that is formed attacks another molecule, so they continue like that. You will always get a radical. If a radical is attacking a molecule, you will get a new radical and then a molecule. But then when two radicals come together, that is what we call the termination step. Okay, the termination, the reaction stops. So we call it the chain. Okay, this is free radical mechanism. It's a chain. We have the chain of reactions. It is only terminated when these ones meet the two radicals. Roman 1, give the name of the mechanism for this reaction. I've already said it. Free radical. Free radical substitution mechanism. Set the essential condition required for the initiation step of the reaction, UV light. I already said it. UV light. And then give Roman 3, we are told to give the electronic configuration of chlorine. This radical here, remember, when these two are breaking down under UV light, there are two electrons here which are shared. Each of them takes their one electron there. Okay, so when they take their one electron, chlorine, remember, is in position 17. So it has 17 electrons. You see that? So we have 1s2, then 2s2, 2p6. These are 10. Then we are remaining with 7. So 3s2, then 3p5. Okay, then from there, Roman 4, they are saying identify the products of the step labeled propagation 2. So for this one here, what is going to happen is this. You have a chlorine and then a chlorine. Then you have this CH2, Cl. It's a radical. So this one breaks while sharing that electron here, even this one here, as this one also breaks off. Then that means that we are going to have a radical comes off from here, which is Cl with that dot, then plus. Now we shall have CH2, then Cl2, two of them, okay? Two chlorines, because already we have one here, so plus one that is coming from here, then you get the 2, okay? So that means we are going to have CH2, Cl2, then this one here, the radical, okay? And then Roman 5, name the type of reaction shown in the final step. I already said it. The final step, the two radicals coming together, that is termination. So just put here termination. And then 6 here, suggest the identity of another organic molecule that is a product of the reaction of this and chlorine under the same conditions. Okay. Suggest the identity of another organic molecule that is a product. So we have many products, by the way. Since here we are getting CH2, this one can continue chlorine until it has substituted all the hydrogens. So I can substitute one more hydrogen here with a chlorine, okay? One more hydrogen here with a chlorine, and then I write CH, then Cl3, okay? I can have CH2, okay? CH2, Cl, again another CH2, Cl, okay? How does this one come about? Suppose I have this radical here, and I also get another radical, CH2, Cl. Okay, these two radicals come into contact. You are going to get CH2, Cl, CH2, Cl. Okay, if I have this CHCl2 here, okay, what we are having where? Here, okay, that radical. Then that radical comes into contact with another chlorine radical. You see? So we are going to get here CHCl3. That's why I've written this one here. You see that? So any of the two can work.